we'll get started here soon. Just gonna give everyone else a little bit longer to show up. So yeah, just wait on for that. All right, let's go ahead and get things started. Not sure where everyone is. It probably has to do with Christmas being so soon and everything like that. But I'm not too worried about it. We do take the recording after all. Yeah. So what we have here is we have ourselves the last, well, not the last. We still have a couple more sections in chapter 7. But I think that what we're going to do is we're just going to go ahead and finish up this one chapter and then call it a day, because I don't think we'll have enough time to, do this chapter plus another one. I think that we'll just go ahead and do this one and call it a day. And then, at that point, don't worry too much about it, because the last thing I want to do is start up a chapter and then, you guys will have to take we'll have a 3-week break, and then you'll come back and basically have forgotten everything, right? So I don't want to do that. So I just want to wrap up this chapter, and then you guys can, well, you guys shouldn't forget it, but you guys can, like, it won't be as bad as being in the middle of a section and just forgetting everything from the earlier part. I that's the last thing I want to do. So what we're going to do is, we're going to go ahead and go through this one section, and then if I think we have enough time for the next one, I might do it and then just kind of try to finish that one as well, but I doubt we'll have time for it. So with that being said, section 7.4. So far in chapter 7, we talked about 2 different kinds of special points, right? The 2 different points that we've talked about so far have been, actually, what 2? Let's see. Brendan, which 2 points have we talked about in a triangle so far?
I just came on. I'm here.
Yeah, but this is a review problem, so you should know that, right?
Wait, what was the question again?
Yeah, so the question is, which points of a triangle, like the special points, right? Which points of a triangle have we talked about so far?
Circumcenter?
Circumcenter? Yeah,
yeah,
we definitely
circumcenter.
We did talk about that.
Wasn't there one something vertex?
Vertices are the points on the triangle, so they're the 3 points that make up the triangle. So not quite.
Wait, circumcenter was one, right?
Circumcenter is one. You already listed that.
In center.
In-center.
There you go. In center.
So 2 points are circumcenter and in-center. Isabella, how do you make those? Like, how do you get them?
So circumcenter is like the lines that reach into the middle for an equilateral, and I think under for the.
Okay, I know what you're trying to say. I know what you're trying to say, but that's not how you find them. More specifically, there's a very specific method that you use in order to find where the circumcenter is. There's a very specific method.
Oh, is it angle bisectors, and then you get, wait, no, that's in center.
Angle bisectors in center. That would have been the next question, but right, that's it. So then in that case, then what is the circumcenter made from?
Oh, okay. So circumcenter is, I think, halfway for each equilateral. And
there's a method that is the same no matter what triangle you're using.
Oh, it's the altitude and
The altitudes?
Side.
Not quite.
Oh, then I'm so confused.
You're confused? You just forgot about it. Brendan, do you remember? How do you get the circumcenter?
Isn't it like isn't it like draw like bisectors, I think? Was it like bisectors?
What bisectors? Bisectors very vague. Angle bisectors, side like what are you drawing here?
I remember there was like 3 bisectors. I think it was perpendicular.
Perpendicular bisectors is
Yeah,
correct. So you take
perpendicular
the
bisectors.
sides,
Yeah.
you take the 3 sides, you draw the perpendicular bisectors of each one, and that's how you get your circumcenter. So now we have the 2 points, and we have this, the ways to get those 2 points. We have circumcenter and incenter. Those are the 2 points. Circumcenter is created with perpendicular bisectors of your 3 sides. Incenter is created with your 3 angle bisectors. No matter what, your incenter is always inside of your triangle. Sometimes your circumcenter is actually outside of your triangle. We proved that in section 7.2. We showed that if you have an obtuse triangle, it actually ends up being outside. All right. Now, Gracie, what is important about your incenter? We talked about how it's made, and we said that it's one of your important parts, but why do we care about it so much? What properties does it have?
It's the middle part of the circle and the triangle.
What circle?
The inner circle.
The inner circle? What's it called?
The inscribed circle.
Right. So the circle that just fits barely inside your triangle, that's going to be your incircle, the one that's inside of your triangle, right? And for this circle, the center of that circle is going to be your incenter. Now, what is your incenter equal distance away from?
What?
What is your incenter equal distance away from in a triangle? So if I draw a triangle, draw the incircle.
The bisectors?
Not quite. It's equal distance away from all 3 of your sides of your triangle, right? So the incenter is the point that is equal distance away from all 3 sides of the triangle, because all 3 of these sides, right? It's all touching on your incircle. And since it's touching, that means it's a radius. And since it's a radius, it means it's always equal distance away. All right, now Allison, what about the circum circle? The one that looks like this. What's unique about this and the circumcenter?
The radius is the points on from the middle radius. Radius is the middle points all the way to the farthest point of the triangle, I guess.
Sure. So this
Angle
point right here
bisectors.
would, sorry, and it's not necessarily angle bisectors. It just so happened that because I drew an equilateral triangle, it was, so it's a little bit misleading. This is only because it's an equilateral triangle. But now, what you can see here though is that these 3 different distances are all the same, right? So the distance from your circumcenter to your outer edges to the outside points of your triangle, right? To the 3 points of your triangle, these are always consistent in a circumcenter. But all right, so that's really it. Those are the big things from what we learned in section 7.2 and 7.3. And it seems pretty intense, right? There's a lot of things to remember about these 2 special points. What if I told you there's 2 more? So our next one is going to be a median, and we're going to talk about what this has to do with anything. So if you take a triangle, and you draw out the 3 different midpoints, one right here, one right here, and one right over here, something like that. What we learned about was that, hey, if we take the perpendicular bisector of these, it always intersects, right? It always intersects at a single point, in this case, this point right here. But we're not interested in that anymore. We already know what to do with that. Instead, what happens if we start from the opposite point on the triangle, so the point that's actually a point of the triangle, and then go to the midpoint and create this line instead? It's not necessarily a perpendicular bisector because this line is not necessarily perpendicular with the base. But if we draw all 3 of them out, we notice that it looks like it meets at a single point. In fact, it always does. And we call this point right here our centroid of our triangle. So in this here, the yellow lines that we've drawn are called medians. The purple dots, the purple points on the triangle, these are all midpoints. So in the problems in this section, there's going to be a couple things that we're going to be able to show. First off, so a couple things. First off, you can assume that your medians will always intersect at a single point. In other words, they will always have a single point that that is on all 3. You don't have to worry about proving that. We'll actually prove it ourselves in a later chapter, but don't worry about that too much. But apart from that, we're going to prove a lot of things about this. So any questions so far? So any questions about what a median is? Any questions about what a centroid is? Anything like that? We're going to prove.
I have a question.
Oh, yeah, sure. Go for it.
So the middle part's a centroid and the yellow lines are median. And then the other purple things are midpoints, right?
Yes.
Yes. Okay, thank you.
Yeah, so then the other things that we're going to find about this are all going to be interesting things about it. Brandon, you have a question about it too?
The yellow one's the median, right?
Yes.
And then the purple one is centroid.
The purple one in the middle is the centroid. The purple points on the outside are midpoints of the side.
Okay, thank you.
And then for Serena, can a median also be an angle bisector? It can happen to be the same point. It is not very common. Does that answer your question, Serena? In fact, this only happens when you're working with a what's it called? This only ever happens when you're working with an isosceles triangle. I want to say that that's the case. From my history, from like my memory, that's what needs to happen. And in fact, if it's an angle bisector and the median at the same time, it also ends up being a perpendicular bisector too. So just a little bit of what happens there. So as you can see this specifically when you have an isosceles triangle like this, for example, this line straight down the middle, this is both an angle bisector and a median and a perpendicular bisector. And then very, very specifically, if you have an equilateral triangle, all 3 of these are all medians, angle bisectors, perpendicular bisectors, and altitudes all at the same time. So it can happen. It's just not very common. But yeah. And then, of course, if that does happen in an equilateral triangle, it happens that all 4 of the points that we're going to be talking about, so the centroid, circumcenter, incenter, and the last one that we're going to talk about is called the orthocenter, but we'll get back to that later. It turns out that all 4 of these points are the exact same point in an equilateral triangle. All right, so with that being said, we're going to learn more about that later on, but we're going to go ahead and look at the problems here. Okay, problems 7.16 through 7.19. So in this problem, we want to prove a couple things. We want to prove that the medians of a triangle divides the triangle into 6 triangles of equal area. Say triangle a couple times fast. We want to make a lot of use of an idea, which is that if you have the same base and the same height, you have to have the same area. Okay, let's take a look at this triangle over here, ABC. This way I don't have to draw a triangle. Serena, let's have you help me out here. All right. So if we have over here, and the reason why I cut it off is because I don't want you to actually use it. I want you to kind of like, I don't want you to go off of what's being listed over there. I want you to kind of think about this with me. All right. So if we have this over here, if we have that point CD is the same as DB, right? This is the reason why this is the case is because this point in the middle is going to be a midpoint. This point is a midpoint, and this point is a midpoint. So what we have is CD is equal to DB. We have FB is equal to AF, and then we have CE is equal to EA. Look good so far, Serena? Okay. So we know that this, so what we've said is this part right here, this area is going to be equal to X. Can you tell me another triangle that has to have the same area as this triangle right here? So DBG, CGD. So why does this triangle over here need to have the same area? Can you explain that real quick? Because CD equals DB. Yeah, CD, this length over here is equal to this. These are both used as the bases in the area of the triangle, right? So the base are the exact same. Now, what about the height? So DG isn't exactly the height because we don't know if DG is perpendicular or not. But what we do know is that both of these triangles use the distance from, this line here to this point. So they use an altitude somewhere like this, but they both use the same altitude, right? Because they both share the same line as their base, right? And then they both use the same final point as their triangle. So is everyone okay with this idea here, that these two triangles must have the same area due to these two reasons? Because the base is the same and they must use the same height. They must use the same altitude. Is everyone good with that? Okay, so now that we have two blue areas, we know that these two blue areas must be of equal value. What about our red? What about our Z over here? What must it be equal to? GFB, right? This part over here must be of equal area as well. For very much the same reasons, go ahead and just list out what base must be the same. Well, we have AF and FB, right? Those two things must be equal. And lastly, we have our orange areas. Okay, we have this over here, Y. So Y is going to be orange. What triangle must it be equal to over here? GEA, that's right. And I agree with you here. Are there any questions on why any of these three pairs of triangles must be congruent and must be not congruent, must be equal in their areas? Are there any questions in this? No questions here? All right. Now, Serena, what happens if we look at things on a little bit of a bigger scale? So we showed that, you know, these two triangles needed to be the same area, right? But what if we look at a bigger triangle? How about half of the whole triangle? Let's look at this one over here. This triangle right here. Is there any triangle here that needs to have the same area as ACD? ADB, right? So ACD and ADB must have the same area. Why? Because they share the same base, right? CD and DB are the same value, right? We know that these two lengths must be the same. And they also share the same altitude, right? Because they both use this line over here as a base and this point up here as an altitude. Well, there's only a single distance away between a point and a line. So that distance needs to be the same for both of the triangles. So now we know that the big triangles, this and this, these two things are equal values. So what we know now is that 2 times the orange is equal to blue, 2 times the orange plus blue is equal to blue plus 2 times red. So let's write all that down here. We have 2 orange plus blue is equal to 2 times red plus blue. Well, at this point, you would just subtract blue away from both sides, divide by 2 on both sides. And what do we get here, Serena? Yeah, we find that, well, I was saying orange, but yeah, now you find that your red is actually equal to your orange, right? So those two things are the same. Red equals orange. And now, Serena, what can we do now to find out anything else that this might be equal to? Due to two big triangles, CAF and CFB. Again, these two triangles must be congruent due to the fact that they share the same value as the base and same height of the triangle, right? This gets me that 2 times my orange plus red is equal to 2 times blue plus red. I'm a little bit lazy to write it out, but you can see that if you just subtract the red from both of them, you get 2 times orange equals 2 times blue. Divided by 2 on each side, you get orange equals blue now. So what we actually find is that each and every single one of these individual triangles of the 6 must be of the exact same area. Any questions here from anyone? So what we know is that every single piece here, every single little triangle must have the exact same area. This triangle right here is the same area as this triangle over here, which is the same area as this triangle over here. All of them have the same areas. It seemed a little bit impossible. It seemed like they looked all different, but it turns out that they are, well, not quite the same because they are different shapes, but the areas are all the same. Nice work. Let's go ahead and take a look at the next problem. Use triangles AGB and DGB in the previous problem to prove that the centroid cuts each median in a 2-to-1 ratio. Specifically, we want to find that AG divided by GD is equal to 2/1. All right. Luke, have you been in this class before?
I'm just watching.
Okay. All right. In that case, then let's have Isabella. Let's have you help me out here. So, one sec. What we want to prove is that the end goal here is we want to prove that AG divided by GD is equal to 2/1. All right. This is the end goal here. All right. Any ideas on what we can do here? We wanted to use these two triangles somehow, some way. Actually, it was these two triangles. So this triangle here versus the big one. Any thoughts?
Can you use similar triangles?
Not quite. So similar triangles only works if their shape is the same, but their ratios are different, or like their sizes are different. But these two triangles don't even have the same shape at all. So there's nothing that you can really do there.
So AG is equal to 2GD.
Well, that's what you're
don't
trying
know.
to prove. It's a little hard to
Right.
it's a little hard to start from there.
Yeah, I don't know.
You don't know? So what you can do here is think about it a little bit differently. do these two triangles share anything when it comes to, you know, their areas? What do we know about the ratio of their areas?
Can you show the problem again?
So the end goal is we just want to show this. Like we want to prove that the median, which is the centroid, so this point right in the middle, we want to prove that centroid cuts the median into a ratio of 2 to 1. That's all it says.
Yeah.
It doesn't actually have very much help for you.
They're both sharing the same base and the same height.
Do they share the same height though? And the same base? When you say base, do you mean do the bases share like a length? Like they share along the line?
They're sharing the same base, but they're not sharing the same height.
Okay, so you're saying that this right here is my base, and then these two things have a different height, right? Is that what you're saying?
Sort of. Yeah.
Sort of? Okay. Okay. But that doesn't actually help us out very much, because if we look at it, because that actually doesn't give us anything about GD or AD, right? Because we're not using GD or AD at all if we do things that way, right? We would be comparing BD and some heights that we have no information about. Does that make sense?
Yeah.
So let's use GD and AD in our area equation somehow. So if we use these two values in our area calculation, right? If we use these two values here, this one and this one, what do we know about them? They're on the same line, right?
Yeah, we know that they're on the same line, yeah.
And the final point is over here, right?
Yes.
So if they're collinear and the final point is over here, then shouldn't they have the same height? The same, something like this? The height's going to be the same, right?
Yeah.
Okay, so we have the same height. Now we're just looking for the ratio of the bases. Well, how do we find that? Well, let's look at the ratio of the areas first. What's the ratio of my areas? So what's the area of my small little triangle here?
It's GD times DB.
Well, not
over 2.
necessarily DB, because we don't know it's a right angle, right? But we know that this value is some value, right? We know that this is some sort of X, right? Well, let me ask you, what is the area of triangle GFB? What is this triangle's area over here?
Is it Y plus V?
It's not, well, just this one orange spot. What did we prove in the last problem?
We proved that CAG is the same as BAG.
CAG is the same as BAG. Yes and no. There was something else there was something more specific at the very end that we said. Do you remember what that was?
Is it like when you said that CEG is the same as BGF and GAE is the same as GAF?
Well, I said it a little bit more broadly. I said that each and every single one of the individual 6 smaller triangles here are all equal in area.
Oh yeah.
Right.
Yeah.
So if this triangle right here, the small purple one right here, compared to this big one, right? Well, isn't this big one just 3 of the smaller triangles? Right? The big triangle
they're
here.
all technically X.
Well, each and every one of the small triangles is an X. Right? So this one is X, this one is X, and this one is X. So the big triangle's area is 3x. And the small triangle's area is just x alone. Does that make sense?
Yeah, so the ratio would be from the big triangle to the small triangle, it'd be 2 to 1.
Why is it 2 to 1 when there's 3 of them?
Wait, I thought we were comparing the small triangle to the medium triangle.
We're just comparing the small triangle DGB, so this triangle right here, we're comparing that to ADB.
Oh, then it'd be 3 to 1.
You could also do AGB, and if you did that, then what would your ratio be?
2 to 1.
Okay. Do you agree with me that for this triangle right here, it also uses the same height because we're still using the same line as our base and the same point out here? Do you agree with me on that? We're still using the same height.
Yes.
Okay. So we're still using the same height here. It's just not inside the triangle or anything like that. Well, if our areas are base times height over 2 and base times height over 2, and we know that the two heights must be the same, and we know that this over here is equal to 2 times this area over here, well, then first off, what we can do is we can multiply both sides by 2 to get rid of this over 2 nonsense. We can divide by h because both sides, both h's are the exact same. So this gets me 2 times blue b is equal to b, red b. Well, let me ask you, Isabella, what is red b? What is the value of my red base? How long is that?
That's AD.
Well, the medium triangle here now. That's the one that
Oh, okay. Then it'd just be the length of AG.
AG is equal to 2 times
2 times the base, so 2GD.
and now if you
Oh,
divide
so we
both sides
proved
by
it.
GD, what do you get?
Yeah, so you just proved it.
So here we get AG over GD equals 2 over 1. And that's the idea here. So all we did was I was originally wanting us to compare the big triangle here to the smaller one and then say, oh, you can just subtract the 1 here. But I think it's a little bit more direct if we compare the red triangle here to the purple one. I think that's a little bit more direct. But yeah, the general idea is each individual small part in there is the exact same. So then it's just going to be a 2 to 1 here. Nice work. Any questions about this proof here? So don't worry about this proof if you didn't quite understand it, because you're never going to actually have to prove something like this in school. You're just going to work with the result. And the result of it is that your centroid cuts your median in a ratio of 2 to 1. And all we did here was we used the ratio of the areas in order to find that. So the side that it's closer to is always going to be the 1. The side that it's further from is going to be the 2. So just remember that if you have a median and you have your centroid, you cut it in a ratio of 2 to 1. That's all that we're showing here. And this is helpful because we can actually use this in order to find some lengths, right? So if we need to find some lengths, say for example, in problem 7.18, we want to find some lengths here. We want to find the lengths of an in radius. And Serena, this is an example where of what you were mentioning earlier, right? I had already mentioned that yes, it is true that this median is also an angle bisector, but we want to prove it this time. All right. Allison, let's have you work on this one. Allison?
I just disconnected.
Okay. Did you get to hear the most of the last problem?
Yeah, but I don't know why there's another triangle now.
We're working with an equilateral triangle now instead. That's why. So first off, we want to show that each angle bisector is also a median here. So how can we prove that here?
plot a point that splits C, E, or any of the lines on the triangle into half, and then
That's a bad color. Okay, so I've drawn the angle bisectors here, okay? We want to prove that these are medians. We have to go in this order. We cannot prove that medians are angle bisectors. That's not what the question states, actually. The question wants us to show that angle bisectors are medians. Does that make sense? There's a bit of a difference, right? Think about the statement like, show that if you live in California, you also live in the US, right? That's easy. But show that if you live in the US, you also live in California, that's not necessarily true, right? So it's very important that the direction that you go is consistent. Does that make sense? So that's why we need to start with angle bisectors and end with median. Okay. So if we start with angle bisectors, we get a couple of important information, a couple bits of important information. We know that these two angles must be the same. In fact, it's also equal to these two. It's also equal to these two. Why is that the case?
30, because equilateral is always 60-degree angle.
Yep, exactly. So now what we know is that we have a 30-degree angle here, a 60-degree angle here. So what does that mean this final angle right here needs to be?
90.
90 degrees. I agree. And same thing over here, right? This one over here also needs to be 90 degrees, right?
Mhm.
So what can we do between these two triangles? The one on the left and the one on the right.
I feel like AX is the height that
Sure, AX is the shared side, it's the height. What else do we know? Not sure?
besides that those two triangles are the exact same.
Yeah, no, that's what we care about. These two triangles are the exact same because they're congruent. You can prove that they're congruent due to a couple different ways. The easiest way would have been actually to use ASA triangle congruency with this side and the two angles there. Does that look good to you, Allison? Okay, so these two triangles are congruent. That means that this length here is equal to this length, which means that point X is a midpoint, which means that this right here is a median. Does that all look good to you here?
Yeah.
Okay. Now what we care about is we care about the in radius of this circle. Well, that's going to be the distance from D to X. Would you agree? Okay, so we want to care about this radius here. How do we find it? What can we do to find it?
Can we use the 2-to-1 ratio thing or no?
So what exactly is in a 2-to-1 ratio? In this problem, what is in a 2-to-1 ratio?
Is it from point B to point X and then point D to B?
Okay, that is true, yes. But didn't we use the same median in the previous question? Like why are you using two different values now? Like you're using two different medians to compare.
Or A to D?
Yeah. And the distance from A to D, how do we represent that with notation?
I mean line AB.
We don't say line if we're talking about a distance. We just say AD. So AD over DX, and then this is supposedly equal to 2-to-1. And I agree with you, right? Because the centroid cuts your median in a ratio of 2-to-1. Okay. So then what we also need then is the total length of the median. Would you agree? Okay. So if the total length of the median is, these two things added together, what is the total length of the median going to be then?
In ratios,
So what would
X to over DX is 3/1.
Right, and I agree with you because the distance of AX is just AD plus DX. So then it would just be the 2 plus the 1, which gives me 3 here. All right, so that sounds all great. Now we just need to know how long is AX? Well, you actually know one more thing, right? Can you read the question back up here again?
Side length of 12.
So what exactly is 12 here?
The hypotenuse is
So AB, right? AB is 12. I agree. So what does that make X be? Actually, what specific
Half.
triangle was this again?
equilateral, so half 12.
Well, this half right here is not equilateral. What is this half right here?
Right?
Yes, it is, but is it any special kind of right triangle?
30, 60, 90.
Yeah, and what are the 3 side length ratios in a 30, 60, 90? Not sure?
Forgot.
You forgot? Gracie, any help?
6, 9, 12.
Not quite. Isabella, do you remember?
Yeah, so one side's 2x, and then one side's x, and then the other side is x root 3.
So if you know that your 12 is your 2x, then Allison, what must your x be down here?
6.
6, right? Then what must your x root 3 be?
6 root 3.
Okay, so what exactly is 6 root 3 here? What value? AX, DX, is it neither of these? What is 6 root 3?
X.
AX is 6 root 3. So what does that mean DX must be?
2 root 3.
That's exactly it. Any questions here? All right, that's it. That's all you had to do here. So what we're really showing here is that if you
What
have
was the final answer?
2 root 3. So
And
all we're
that's for
showing,
dx, right?
yeah, DX, which is the value of your in radius right here.
Okay, thank you.
Yeah, no problem. But yeah, so the general idea here is just if you have, medians to work with and you have your centroid, you can use this ratio. If you know the value of your median, if you know how long that is, you can actually find out the parts of it too. This will usually come up in equilateral triangles. It's very rare. It's very, very rare that you would ever use this for anything else. All right, that's going to be it here. All right, 7.19. Am I good to erase? Hopefully. All right. 7.19. So for this problem, we just want to show a couple things. We want to show that these 4 individual triangles that we've made by connecting the medians, by connecting the midpoints, rather than drawing out medians, we want to show that these 4 triangles are also the same value. So earlier on, we showed that if you connected the 3 medians, if you drew out the 3 medians, and then you looked at the 6 different triangles that were created here, these 6 triangles all had the same area. But now what we've done is we've connected the midpoints instead. The 3 midpoints have now all been connected to each other. We want to prove that these 3 triangles, well, these 4 triangles rather, are all the same. Now this same goes a little bit further. We actually want to prove that these triangles are all congruent. Let's see if we can do it. All right. Let's see. Gracie, let's have you help me out here.
Yeah.
So first off, let's start with this triangle in the bottom right. But before we compare it to any of the big triangles, to any of the other triangles specifically, let's find out more information about all of my angles. And in order to do that, we can do it by looking at the big triangle. Any ideas on what that means?
What?
So let's compare this triangle in the bottom right to the bigger one out here. What's the relationship here?
Is it 1/3?
Well, I'm not looking for the ratio. I'm looking for the relationship.
It's 1/4 of the triangle, the larger triangle.
I'm not looking for the ratio. I'm looking for what is the relationship? Are they what triangle relationships have we learned about in so far? We've only really learned about 2. We've learned about congruency and similarity. Well, are they the same size, same shape? Of course not. So what is the only option?
Similar.
Similar. How do we prove that these two triangles are similar? What are my 3 different ways of proving triangles are similar?
Side equals side.
Okay, what's another?
Side, side, side.
And lastly?
Angle, angle, side.
Not angle, angle, side, it's just angle, angle. So we actually know already between my smaller triangle and my bigger triangle here, we already know that this angle here is the same, right? So that throws side, side, side out the door. We're not going to be able to find anything about side, 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 most likely. Because if we already have an angle, it's very hard. It's very doubtful that we're going to find this third side. Okay. Well, can you prove that these two angles are the same? No, you can't. There's nothing nothing that you can do with the information that you're given that you can prove that those two are the same. You cannot do the same thing for these two either. So then that means that throws out angle, angle. So the only thing left is side, angle, side. Side, angle, side similarity works by showing that the ratios of the two sides here and the ratio of the two sides here is the same. And then the angle in the middle is the same. That's how side, angle, side works. So can you show that the ratio of these two sides to these two sides is the same?
Yeah.
What is that ratio?
1/2.
Well, more specifically, this to this is 2 to 1. This to this is also 2 to 1 because, you know, this right here, if this is x and this is x, the whole thing is 2x. This thing here is just x. That ratio is 2 to 1, right? So these ratios are consistent, which means that this smaller triangle is similar to the bigger one. Is everyone good with that? Is everyone good with that idea?
Yeah.
Everyone else also good. Okay. So what we know now is that this angle right here must also be a red angle, and this angle up here must also be a purple angle. Look good to you, Gracie?
Yes.
Okay. And you can repeat the process for every single one of these triangles. You can repeat it for the top triangle. You can get that this angle is a red angle, this angle is an orange angle, and then you can repeat it for the one over here to get that this is an orange angle, this is a purple angle. Well, what you also know is that purple plus red plus orange must equal 180 degrees, correct?
Yeah.
Well, then over here you have purple and red already. So what are you missing right here in the middle?
A circumcenter.
An orange. Because these three angles add up together to equal 180 degrees. So if you have purple and red already, you're just missing orange because you know that those three are the values that add up to 180. Does that make sense?
Yep.
Okay. What angle are you missing here?
Purple.
And what about up here?
Red.
Nice. So now we know that all 4 of these triangles have to be at the bare minimum similar to each other because they all share the same exact angles. But in fact, you can actually go one step further. You can show that each one of these must be congruent. Why? Look at these two triangles right here real quick. Don't they have angle, side, angle? Angle, side, angle. These two triangles are congruent due to angle, side, angle. Sure, the order of the angles is a little bit mixed up, but you can see that it's a red angle, shared side, purple angle, red angle, shared side, purple angle. And then you have the same thing out here. Purple, except it's with purple, orange, and a shared side. And then over here, you have it between red, orange, and a shared side. In fact, all 4 of these triangles are all congruent to each other. So Gracie, let me ask you one final thing. What is the ratio of the area of this triangle to the big one?
1/3.
1/4.
Oh.
Because if each one of these has an area of x, isn't the whole triangle just going to be 4x then?
Yeah.
So then the ratio would then be 1 to 4.
Yes.
Any questions here?
No.
So first off, we use the triangle similarity to show that these triangles were similar to find out more information about our angle measurements. And then from there, we showed that, well, these triangles, this one and this one are congruent, this one and this one are congruent, this one and this one are congruent. And that just shows that all 4 of them are congruent. And if you really wanted to, you can even show that these two lines are parallel. And you could do that by using a transversal line right here hey, these two are alternate interior angles. So that's really just it here. Any questions from anyone about these 4 triangles here? This is what we call a medial triangle. All right, you have a
Is the
question?
medial triangle just EDF?
Yes, it's the one in the middle. Sorry, I should have been a little bit more clear about that. So what we also know is that ED is actually equal to this length right here. This length right here is equal to this length over here. And this length over here is equal to this length over here. That's all that we have here. All right. So let's use this to prove some other problems. Let's take a look at the last 2 problems here. We have problem 7.20 and 7.21. All right, Brendan, 7.20. Triangle ABC has side lengths of 9, AB equals 9, BC equals 12, and CA equals 15. We want to find the length of the median from B to the midpoint of AC. All right, first off, Brendan, what kind of triangle is this? And why did I draw it this way?
It's not. Wait, did I forget it? It's scalene triangle, isn't it?
Sure. I mean, I suppose, but I feel like you've missed the forest for the trees here a little bit.
It's a right triangle.
Why is it a right triangle?
Angle. Well, is it angle B? Angle B has a 90-degree angle.
Well, yeah, I drew it that way, but why do we know it is from the information that we've been given? We surely have not been told that this is a right triangle, but why do I know it's a right triangle?
I don't know.
You don't know?
I don't think I can remember it.
You don't think you can remember? Serena, help him out. Why do we know that this is a right triangle right away? Serena? Probably is typing. Just came back. Okay. Okay, so why do we know that triangle ABC from the information that we've been given up here? Why do we know that it is a right triangle? Gracie, that's not necessarily true. I drew it that way. Okay, you're saying it's a 3, 4, 5. I don't see 3, 4, 5 though. I see 9, 12, 15. Oh, if you divide by 3? Yeah. So if you divide by 3, this actually ends up being a 3, 4, 5 triangle. And what we learned earlier on in chapter 6 was that if you have triangles with sides of 3, 4, 5, or any multiple of that, it's always a right triangle because 3, 4, 5 is a Pythagorean triple. We also learned that anything with 5, 12, 13, and 7, 24, 25, all of these will also work too. So this is just a 3, 4, 5 multiplied by 3. So this 9, 12, 15 has to be a right triangle due to the fact that it's a 3, 4, 5. Okay, so now that we know this is a right triangle, how does this help us out? If we go for the median here, how does that help us out at all?
Is it still me?
Yeah, still you. You just got helped out in that part. The rest of the problem is still you. Let's call this point 0. What do we know about this?
0.0.
What have we learned about the midpoint of the hypotenuse of a right triangle? Have we learned anything about that?
I think we did the midpoint of a hypotenuse is the circumcenter?
It is the circumcenter. Nice work, you remembered that. So if you know that this is the circumcenter, what do you remember about the circumcenter? What is the equal distance away from?
What was it?
What is the circumcenter equal distance away from?
The circumcenter is the equal distance from the vertex or the points?
The points on your triangle. That's right.
Yeah.
That is exactly right. So if it's equal distance away from A and O, so if OA is the same as OC, which is the same as OB. Well, first off, what is OC? What is the length there?
7.5?
Yeah, 7.5. So if that's equal to OB, then what does OB need to be?
7.5.
That's it. This question is really simple, right?
Yeah.
As long as you remember all the properties, this question is very simple. If you don't remember the properties, you're in for a nightmare because you have no idea what to do for anything here. But does that make sense, Brendan?
Yeah, it does.
You just piece together the puzzle pieces, and that's how you get your information. You just have to make use of all the different properties. So that's how important this is. This section, I promise you, is not very hard. All you have to do is remember the properties of the points. Remember and understand what these all mean. And as long as you understand that, these questions are not hard at all. And I'll wrap us up here for today for problem 7.21. Just making sure I've asked everyone a question at this point, right? Like I've had everyone else work out a problem here. I know, Luke, I haven't asked you, but you said you were just listening in. Okay. All right, problem 7.21. In triangle JKL, we're told that JK is equal to JL, which is equal to 10. So let's go ahead and mark that out. These lengths are 10 over here, 10 and 10. Okay. We're looking for the median of JM. So we're looking for, first off, the length of JM over here. And at the very end, we're going to look for KN. So we know that KL is equal to 16, but because we know that JM is a median, we know that JM right here, well, that means that this must be 8 and this must be 8. Well, wait, doesn't that mean that this thing right here doesn't that just mean that that's going to be 6? Because this right here is just a, well, that's a 3, 4, 5, isn't it? Right? We have the ratios of 4 and 5 over here. So that means we're just missing the 3 and we have 2 times that stuff. So that's going to be a 6 right here. So if we know that this is 6, then we know that GM down here needs to be 2, right? Because we know that the ratio of the bottom part, the shorter part to the whole thing is 1 to 3. So that means that we know that GM is just 2. Well, what we also know is that we're looking at the median of this triangle right here. This is an isosceles triangle. Medians of an isosceles triangle always meet at a 90-degree angle. So we're looking at a right triangle over here. So if we know that we're looking at a right triangle over here, we can find KG by using the Pythagorean theorem. The Pythagorean theorem says that KG squared is equal to 8 squared plus 2 squared, which is equal to 68, which means that KG is equal to the square root of 68, which is equal to 4 times 17. So this is equal to 2 root 17. So what is Kn then? Well, Kn is equal to 3 times that divided by 2, because the ratio of Kg to Kn is 2 to 3. So I just do this times 3 over 2, and I get my answer of 3 root 17 is equal to Kn. I know I went through that really quickly, but I promise you, if you are very, very solid with your understanding of what all of these different properties mean, this is how fast this question should take you. It should not take you very long, because you should be able to see, wait, oh, this is a right angle right here, because I know that medians of isosceles triangles meet at right angles with the base. Oh, I know that if this, I have 10 and 8 here, this has to be 6. I don't even need to do any actual math. Okay, if this is 6, then I know that GM down here is 2. And I know that this triangle over here was a right triangle. That means I can find KG with Pythagorean theorem. And that means I can find Kn with my ratios again. That's really just it here. So with all that being said, that's going to be it here for chapter 7. That's all for chapter 7.4. We still have a little bit left in the rest of chapter 7 that we're going to talk about in the new year. But for here, homework is just going to be exercises 7.4, chapter 7. Section 7.4 exercises. And with that, I'll see you all in the new year. If you have any questions, feel free to ask. If not, then I'll see you guys next time. All right. Yeah, for sure.
When is the next class then?
Next class is going to be January, I want to say 15th.
Okay, thank you.
Yeah, so 3 weeks of break and then January 15th. All right. See you guys next time.
Bye.
Bye. Have a good New
Bye.
Year. See you next year.
See ya.
Yeah, for sure. See ya.